kids, how's it going? How's everybody doing? How are you doing?
I'm doing pretty good.
How am I doing?
I don't know. How are you doing?
I'm doing all right. Not bad. Not bad, buddy. Let's do the thing we call...
What happened last time?
Well, last time we worked on redo, and I think we finished up undo. And we also, wait, let's see. What else did we do?
Hairdo. Sorry.
Oh, I'm forgetting. Do you remember what we did?
Yeah, we started working a little bit on the that other new logic piece. We've just added a little bit of what I call pseudocode into the code. Not real code, but we put some comments in the code, saying where we were going to go. We also made it so that you could click anywhere and it would solve the focus problem.
Oh yeah.
Right?
The focus would come here.
Yeah.
And
So
you can also use the arrow keys and
right.
then click back here.
Yep.
And the focus will be there or here.
We did that. We also made it so undo and redo also adjusted that location piece as you go. So if you were to type in 1, 2, 3, let's just demonstrate undo and redo.
1, 2, 3. And then if I hit Control Z, 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 and then also we can do Control Y or Control Shift Z.
For redo.
Yes, for redo.
Right.
And it brings our cursor to that place. So if I just Control.
So see the yellow block there, it's just moving that highlight block around based on where he was when he made that change.
So if I do a 1 here, and then a 2 here, and then up here I do a 3. Right now we can, if I Control Z, it brings the selection.
And then Control Y or Control Shift Z back.
Yeah.
Yeah, it's cool. Yeah, it's cool. I like it. That's what we did last time. We have one more logic piece that we've been thinking about adding. We're not sure if it's going to do any good or not. So we took some benchmarks last time. Can we show them that document?
I have them. So for the easy game, we can do it in 3 clicks of the solve button. Game, it's 9 clicks of the solve button. For the hard game, it's 7 clicks of the solve button, and then 1 hint, and then and then 3 more clicks of the solve button. And then for the expert game, for the expert game, we can only click twice on the solve button, and then we hit a block, and we have to use 1 hint, which is kind of like brute force, but for one square. Which took approximately 10 minutes, and then it's a lot.
Took a lot of time. Yeah. There are many combinations. I think we can reduce that time. There's a number of strategies we can do to go after performance. I'm glad that we took this. We kind of have a rough sense of what it takes. The expert game took several brute force attacks, meaning every time we have the word hint in there, meaning our regular human emulated logic wasn't able to figure it out. So we had to then just throw everything at the board to solve it, then roll everything backwards, and then pick one of those. Yeah,
there's something that I think we have to add to our brute force attack and our hint button, and that is, we talked about this a bit before, and that is to implement our regular logic as well into the brute force, so it will try something. And then once it tries that one thing, it will try all of the logic, and if that works, then basically. Does that make sense?
Yeah, it does. I'm not exactly quite sure how to do it yet. I need to kind of look at that code. But yeah, that's definitely a thing that we were talking about doing. Switch back over here to my machine. Here's the place where we were talking about adding the new code. And just to kind of quickly review that, we went over this yesterday. But the idea is that if I have like a 1 and a 2 here in this square, a 2 and a 3 here, and a 1 and a 3 in this square right here, what that means is among those 3 squares, the 1, the 2, and the 3 are going to be there. What we can do is we can take the union of these two. Do you know what union means?
Yes, I think so. It's kind of a group that is. No, I'm not sure actually.
All right, let's start talking about set theory. Set theory is kind of stuff we already kind of innately understand because we see those things, but it kind of goes like this. If I have this over here, okay, let's not distinguish these. Let's distinguish them differently by shape. Okay, and then let's change the background border color. Cool. So if I want to take the union of these two shapes, right? The union of this and that, right? Equals, as you might guess, kind of like when you talk about people getting married, we call it a union. Does that make sense?
Oh, okay, that's simple.
Okay, so there's one. That's called union. Okay, there's set there. Let's put the word union out here actually. So that's union. Union essentially means addition.
Yeah.
Right? We're adding everything up. What we call it union. So let's look at this union. Let's move this right. You know that and that equals this. Okay, cool. All right, let's do another one here. Intersection. This is kind of not really related to any operators you've learned yet. I'm just going to write down what's in common. So the intersection of that and that equals the empty set. And I just want to get, so that's the answer right there. Let's make that nice and big. In other words, there's nothing in the set. Does that make sense? It's equivalent to zero. The empty set is zero in set theory. What'd you say?
The fact that they have nothing in common? Or?
Right, there's nothing in common there. Let me change the color on this to further distinguish this.
So what are the things they would look for in common?
What'd you say?
Like, what are the things in the intersection that you look for to be
Let me give you another example of intersection.
in common? Yeah, but I mean like in numbers. What would it be
What would be an example?
Yeah.
Some of your friends got a cat and two dogs, and you've got two mice and a cat. What's the intersection? It's a cat. What do you have in common?
Okay.
What's in common? Okay. So here I've got three of these and one here, right? And there's the intersection of that, right? If I were to duplicate this and say, okay, let's throw one more over here like that, then I get
Then
to
it
throw
would be
one
two.
more down. Whoops. I get to throw one more down here, like that. Does that make sense?
Yes.
And if I were to throw one of these over here, then we get another one down here, right there. I just gotta move the word "and" over. Starting to make sense?
Yeah.
All right, so we've got union, intersection, and let's duplicate the slide. And now we're gonna talk about subtraction. And subtraction, just like subtraction with integers or with numbers, there's a target and a source. The target comes first, and the source is the thing we're subtracting, right? So, and it's useful to label those target and source, I find, because often when we're talking about deltas or vectors, we're trying to get to a target, right? So the question is, which one do we subtract from first? Well, the one we're trying to get to is the one we start with, right?
Oh, okay.
So yeah, that's kind of what it is. If I have to go climb up to, the top of the mountain and the mountain is 100 feet tall, okay, that's my target. I start with 100 feet. I find out where I am, my source, that's me. I'm at 50 feet, and I subtract that. So 100 minus 50 is equal to 50. That means I've got 50 more feet to go. So I always say target minus source when I talk about subtraction, because it helps disambiguate. That's what it does. So now I'm going to call this the subtraction. Oops, of this minus that, right? And minus is maybe not the right word. I guess you could say minus, but the thing is there's no, in set theory, there's no concept of negative elements. So if I'm going to try and take something away that I don't have over here, it just goes to an empty set.
Okay.
Does that make sense?
Yes.
In fact, maybe like this, well, it goes for an empty set for that piece, but you're going to add empty set to the final result is what I guess I really mean. So let me show you what I'm talking about here. So with this right here, let's first of all make it a little bit simpler. So what do you think the answer is to that?
It would be one circle, right? One blue circle.
That's correct. Okay? Good?
Yeah.
So that's subtraction. One more example of subtraction. If we have this minus that, we're still equal to a circle. Because we just can't get rid of it. Okay?
Yeah. Okay.
All right, so that's a little bit about set theory, right? We use set theory. Have you ever seen or heard of a Venn diagram?
Yeah.
Yeah, Venn diagram. Let me just make it real quickly here. Make this transparent. Venn diagrams look like this,
Yes.
right? What's this part right here?
That's what they have in common.
Right. Which of these three set operations we've learned about, union, intersection, or subtraction, gets you this middle piece
Oh,
right
it
here?
wouldn't be the union, it would be the intersection.
Right, it's the intersection. So Venn diagram is essentially talks about what's in the intersection and what's left over on either side. Right? That's typically what a Venn diagram is doing. Now, one of the things that I do in PowerPoint that most people don't do, but I totally do it, is I create these buttons across the top. I'll show them to you in a second. And I use them for shape manipulation. Whoops. Here we go, right here. So if I were to take these two like this, I can come in up here to click these different buttons. One of them is union. What do you think that's going to produce when I click union? Right now, two shapes. So let's do this. Oops, sorry. Do group these for a second. I'm going to drop them down like this. And I'm going to duplicate these couple times down the page. Maybe one more. Let's do this space all the ways. So you're thinking about what we're going to do for union, right?
Yeah. Wouldn't it just be, it would just be that, right? Or?
Wouldn't it be just this, what I already was starting with?
Yeah.
Yeah, kind of, but this dark area here would go away. It's kind of what's happening there. The dark area now is kind of an overlap because both of these have half transparency. So when I put them over each other, right, you can kind of see what's going on there. So what's happening, they're just making it a little darker. But watch this. So we're going to do this. We're going to put the words of all the operations down here, and we'll take a look at visually what they do. Okay? So this one's going to be union. What's the next button down
In
here?
set theory, is there such thing as like negative numbers? Or not really numbers, but as negatives?
No, not to my understanding. There's not. Not that I've learned. There's subtraction right there. Next one over is intersect shapes. Intersect. Next one after intersect is fragment. And just these are different shape operations, but a lot of there's overlap with this. Anything that I missed here, subtraction, intersect, fragment, combine. Combine is the one that we haven't done. And I think combine will have no different effect on from union, is what I think. I'm not entirely sure about that. I don't know. I don't remember what combine does. Okay, so let's try them one at a time. So what I'm going to do is take all of these and move them over here. And now I'm going to do each operation. So one, I'm going to click the left and then the right, then I'm going to click the union button here. There's union. See it?
Oh,
The
yeah.
left, then the right. So this is my source. This is my target minus my source. And I'm going to hit subtract.
No.
See it?
Oh.
The left and then the right. I'm going to come in here and say intersect
It's gonna
shapes.
show the, yeah.
Okay, that's the intersection. The left and then the right, and then I'm going to come up and hit fragment shapes. And look what's happened here.
Oh.
See it?
Oh, that's cool.
That's kind of cool. I'm just going to do this so we can kind of see that a little bit better. The left and then the right. Now I'm going to go hit the combine operation. I'm not sure what's going to happen here. Oh, combine is the opposite of intersection. See it?
That's cool.
Yeah, it's cool. So that's a little bit about set theory. Got it?
Yes.
Okay. Set theory is, and set theory working on shapes, essentially, is the set operations working on shapes. Okay? Cool, cool, cool. All right. So back over here in our code, we've got to do some things here. Actually, maybe before I jump to the code, let's go back and kind of just explain the logic. So logic says, look, I've got 1, 2, 3 squares that have 3 numbers in them. Some of those squares are in B2, some are in B1, and some might be in B3. The rule basically says, look, if I've got 3 squares with 3 numbers, I know those 3 numbers are in those 3 squares. And if some of them, if I can get like a larger number of those numbers in one group than in another, I can infer that some of those may not, the numbers here are absolutely not in these other squares here.
Wait, sorry, can you say that again?
Yeah, I know. This is
It's a bit
tough.
confusing.
It is. I'm so glad you're asking me to do that, though. So the idea is if I can subtract, basically what's happening is I need to do a group subtraction here, a set subtraction. I have to find out what the set of numbers are that's in B2 in this row. So I've got a row, and I'm now that I've found these 3 blocks, I now check to see where those squares are. So I said these 3 squares. I said blocks, I meant squares. So I'm going to take these 3 squares, find out where they are. I've got 2 of them in B2. See, so B2, 2 squares add up to 1, 2, and 3. So I'm unioning these. It's not 1, 2, 3, 3. It's just 1, 2, and 3.
Yeah.
Okay, so I'm doing some set unioning here. I'm going to union everything in this group. I'm going to union everything in this block as well. So here I've just got 1 and 2, right?
Oh, and then you subtract.
Then I do a set subtraction of B2 of my target, which is B2, minus my source, which is B1, and I see is anything left over. If I have anything left over, that means I know there's not a 3 here. That means there has to be a 3 in one of these 2, which means there cannot be a 3 in the rest. So that's how I would explain it. But what I'm also explaining is how do we figure that out? What's the math behind it? And so there's essentially some set math we're going to have to do here. We're going to have to basically. Go ahead.
Sorry, I just realized there's currently a bug in our code then, because if we have a 3x3 rule that's like this, for example, where it's 1, 2, 2, 3, 1, 3, and the 2, 3, and 1, 3 are in one block, the 1, 2, it will block out all of the 3s from being in that block as well, I believe.
Nope, I'm pretty sure it's
because
not.
they're not in the same.
I don't think we have that bug.
Right.
I'm pretty sure we were.
We would only do it in the row. Okay.
I'm pretty sure we were smart enough to figure that one out, and we didn't do it. Yeah,
Because
we're only
it doesn't
doing.
do it for the block unless they're all in the same
Yeah,
block.
it only does it for the row,
Yeah.
right? Yeah, does not for the block. So we're now moving to the next level where we're looking at columns or rows and seeing how they influence blocks or blocks that they are contained in.
Yeah. Vice
Okay.
versa.
So basically I get the example here, I've got 1, 2, and 3 in B2, and I've got 1 and 2 in B1. I subtract B1 away from B2, and I get left over with a 3, which means there's no 3 in the B2s. I reverse the subtraction operation for the sets, and I get the empty set. This is the symbol I'm using for empty set. which is also known as like a 0 like this, but basically it means, look, there's nothing there. Okay? So there's nothing we can do. Does that make sense?
Yeah.
Let's duplicate this for a second. There's kind of another thing, another way I wanted to look at this too, I think. I wanted to make, I wanted to do the example. I wanted to move this over out here to B3, and then I wanted to come over here, make that 1, 2, 3, and just do a little bit of editing there. All right, cool. So I got 1, 2, 3 in the middle. I got 1 and 2 here, and 1 and 3 out here. I want to copy that. Put it between 1 and 3 right over here. It's as if I drew the whole thing, isn't it? Whoops. Right like that. I just want to look at this a second, make sure that everything's still cool. B2 is still 1, 2, 3. B1 is still 1 and 2. B2 minus B1. Here's the problem. When I say B2 minus B1, that's not the full picture. It's B2 minus any other groups that have values. So I have to, this piece right here has to become B2 minus B1 minus B3. And this one has to become, let's see if I got my pen working here. Is my pen working here? Yeah, it's working. That's awesome news. Just move a couple things around here. Hit undo. All right, so this is going to become minus B3. And this is going to become minus B3. And here in both cases now we have the empty set. This one's not this anymore. Funny, I picked up different parts of the letters based on the speed at which I was writing. Okay, so this is going to be the empty set right here.
Okay.
Okay, does that make sense? Whoops.
Yes.
Boom, boom. Place that up there. All right. Because we don't know.
Yeah.
We just don't know anymore. It could be 1, 2, 3. It could be 2, 1, 3. It could be 2, 3, 1. Right? Everything, everything is pretty much all over the place. Is there anything? Am I wrong on this? I just want to double check. Is there any combination here? I kind of like when I do this, I want to go through all the combinations. Let's just play with this a second. Let's throw a table down here. We're going to need 3 columns and a bunch of rows. And we'll just play through all the combinations we have here. So we'll say here's B1. Square root of B1 is going to be, that's going to be B2. And this is going to be square root of B3. And so now we have 1, and then 2, and then that's going to be 3. Next option is 2 here. Well, actually, wait, hold on. There's one more in the 1 column. 1. This could be 3, and that could be 1. That's another one with this being 1. Next, we go to a 2, and then this goes to be a 1 or a 3. So we'll go to 1, and then that means this is a 3, and then we go to it. Still a 2, and then it's a 3, 1, and I think that's all the combinations, is what I think. And so, out of all those combinations, well, we do know that 3 isn't there, but that's not really helpful because we're not able to eliminate anything. We still know only the 1 or 2 are there. It doesn't really help. There's nothing we can infer in B1 with regard to these other squares from these combinations. With B2, it can be 1, 2, or 3. So there's nothing we can infer about this. And over here, it can be 1 or 3. Yeah. So the answer is no. There's nothing we can do if we get the empty set. So the logic still holds here, but basically the piece that we need to know, it's not just one group minus another. It's one group minus the other 2 in the same, in the same row or the same column.
Or even blocks if we reverse the logic.
I'm not sure about that. I haven't even thought about blocks yet.
Well, think about it.
No, I gotta write this first, man. Okay. You'll get me off track. Go ahead.
Okay.
Give it to me.
Well, if you have the block, right? I don't have a very easy way to do this.
Yeah, you want me to draw something for you?
Wait, no, I got it. I can use this.
Okay, switch over to your machine here.
So if you have this block, and in here you have 5. Oh, dang it.
You
I
need
don't.
notes is what you need to do,
I do.
don't you? Yeah. All right, let's go back over to my machine. Let me see if I can get that sorted here. It's pretty much like. Let's grab some squares. I think I have the squares already. Down here. All right, a baby Sudoku square. I like that. Okay, so paste that in. Put the notes here. Make it smaller. Drop the font size down. All right, so we're going to create a block like this.
Yes.
Okay.
Okay.
There's a block.
So
Wait. Let me do one more thing here for a second because I want to show it's part of a bigger thing. All right. Group it a second. I'm going to take this, move it to there, and then move it to there. Stop and do the same thing here. Move it to there, and move it down to there. All right.
Okay, so if you have in the top left corner and the one to the right of that, and if in the notes there you have 1, 2, and 1, 2, or 1, 2, and 1, 3, sorry.
1, 2 here.
And then the one to the right of that, also 1, 2.
Okay. All right.
Or sorry, 1, 3.
1, 3. Okay.
Mistake. And then below that, you have, or below the 1, 3, you have, it would be 2, 3.
2,
Yeah.
3. All right, I'm with you so far.
Then we know that we can block out 1 from the row in which 1, 2, and 1, 3 are. We know that we can block out 1.
Yeah. Yeah, I think I'm with you on that. So let me just draw an arrow here. We know we can eliminate
1 from this
all
row.
ones from this row. That's what we believe is true.
Yes.
That are not in the 3, all other ones, that's what I should say.
And then we also know that in the column that 1, 3 and 2, 3 are in, this is just in this specific example, 3 can't go in that column. You don't have to write that down because it's basically the same logic.
That's not true. 3 does go in this column. It has to because of Sudoku rules.
3 doesn't go in the column, or in the 1, 3 and 2, 3 column. It doesn't go anywhere but that.
Oh, I see. No 3 but here. We can eliminate all other ones from this row, and we can eliminate all other 3s from this column.
Yes.
Right, like that. Right. All other 3s from this column. I think that feels true to me. It does. So we just got to figure out how we're going to do that, what the logic is for that to make that work. That's what we got to do.
Which I guess this kind of feels like the 2 by 2 rule, but different.
No, because it's really, I think we have to absolutely integrate it into our solver n by n.
Oh yes, yes.
Because we need to first get this candidate where I've got 3 squares with only 3 numbers in it, or 4 squares with only 4 numbers in it, or 5 squares with only 5 numbers in it. Right? That's the candidate piece. So this is kind of looking ahead to maybe an additional piece of logic we can add. It feels, I haven't thought about this deeply enough to be like, yeah, you're definitely right on this, but it does feel true to me. It does feel true. Yeah. In fact, now I've now gone a level deeper, and now I'm like, okay, yeah, you know what, you're right. So the thing is, we got to, and again, it's like these 3, to be clear, like these three squares are from our n by n or 3 by 3 algorithm.
And then we can do the same with the 4 by 4 rule and even the 5 by 5 rule. But I don't think the 5 by 5 rule will show up much. And I especially don't think that we'll have a case like this with the 5 by 5.
Well, the cool thing that we're doing, Campbell, is we're putting the logic inside solver n by n, which is the ancestor class. So it doesn't matter. Once we implement it, all our n by n rules will get this. That's the cool thing about inheritance. I'm putting it in the ancestor class, which means all my descendants, they're going to get that data. They're going
It's like having like tubes that go from one cup into a bunch of cups. And then if you pour like soda water, for example, or sparkling water in the top cup, it will go into all of the other cups. And then if you pour just regular water in, it will also go into all of the other cups.
Right. Okay, so these three squares are from our n by n algorithm. There are three squares containing only three numbers in the block. Okay. Containing block 1. Okay? Alright, cool.
There's even probably, there's even a solver 8 by 8 in this. But,
well, I think the problem you get, though, is that once you get to 5, you've now got 4 remaining pieces left.
And the chances of those having any...
those having... you're dropping. You could theoretically, I think, get even into a 7 by 7, right? If I have 7 squares with 7 numbers in them, right? Only those 7 numbers are in those 7 squares, then I know that those 7 squares have to contain those 7 numbers, and that whatever's remaining can't be in the other, those 7 numbers can't be in the other 2 squares.
There's even a 9 by 9 rule, somewhat. There's somewhat of a 9 by 9 rule.
I feel absolutely there's not, because there's nothing left over to work with.
If there's a subset, if there's a subset of the 9 by 9 rule, and we have this rule, this could use the 9 by 9 rule to eliminate numbers from a row. Possibly. But,
I think I see what you're saying. You're saying if the subset being that within the rule I find, hey, a stack of 3s or a row of 1s.
Yeah.
Right? Because that's what's happening here. I've got a row of 1s. This is, by the way, a brilliant example. I really love that you've thought of this and came up with this. Visually, I think it's pretty easy to understand and follow. And it's great because I refused to even explore this idea in my head because I was like, let's implement this math first. Because this is going to be a little tricky, I think, to get this here.
Yeah.
So what do we need to do? We need to collect by group. We need to know which group a square is in. Right now, I don't think we know that, right? Sudoku square.
Well, we know which block, which column, and which row it is in.
Do we?
Yeah, I thought we did.
We do not. Solve for many just passes a group of 9. Remember the call for solve for many? It's passed in here from solve, and solve is called, let's get the call for solve. Here it is. This is that base.
But it has the column.
Logic.
Solve does.
Solve calls get column.
Yeah.
Apply solvers knows where we are.
Oh.
But the solve method doesn't know, it's just getting a column in, or a row, or a block. In either case, these are always the same structure. It's an array of 9 numbers.
Yeah.
Okay? Now what I'm doing though is I'm adding one additional parameter, block, row, and column. What I think we need to do is add one more parameter.
For Sudoku square.
I don't think we need to do any other parameters. What I want to do instead, I want the squares to know what block they're in. I want the square to know what their coordinates are as well. It's not too hard to add that. It's not. So, several times we've got this, we're refresh all nodes, clearing the nodes, quick events, Sudoku board. When do we create a new one of these? I want to go find out where we first create a new one. There it is. In the Sudoku board. So what I want to do here is this is static, which means we never create an instance of it. We just have methods we can call. What I want to do here though is I want to, when we first use this, I want to initialize that. So what I can do is, do you know what a constructor is?
I think we've talked about it before, but I don't remember what it is.
Constructor is a method that's called when you create a new instance of something. It's automatically called. So when I create a new Sudoku, if I had a cookie and I was creating, if I had a class called cookie and I was creating a new instance of a cookie, like a chocolate chip cookie, I could have a constructor that just sets things up. It constructs it. Does that make sense? That's where the name comes from, constructor. There's also a constructor for static classes as well. And there's a template encoder called CCX, which stands for constructor create static. And it just looks like this. It's just the word static, then the name of the class. So it doesn't have a void. There's no void type or string return type. There's no return type on this. And that's how you know it's static. And it's got the word static. That's how you know it's a constructor. A regular constructor looks like this, if I could create an instance of it. But I can't because I called this class static. So it says, hey, static classes cannot have instance constructors. But that's what it would look like if I got rid of the word static here and we were through.
Isn't that just a regular method?
No, because a regular method has a return type. A regular method will have like the word void here or something. And return it. Does that make sense?
Yes.
Or it'll have return a string, like that.
All right.
Okay, that's the difference. So constructor, regular method, and then static constructor. Okay? Looks similar, but that's the distinction. In the static constructor, I want to have that, I'm going to go grab that looping code. Holy cow, do I love those lines of code right there. And I want to come in there like that. And now I want to go through and I want to say, hey, look. Squares of row, comma, column, right? Dot. And what I'm going to say in here is I'm going to say row is equal to row. I'm going to make this one be column is equal to column. Okay? And then I'm going to say what block we're in as well. Block is equal to, now this, I got to do some math. I don't know how to figure out the block yet from these.
We have it, don't we, somewhere?
I don't think we're tracking the numbers anywhere, no. So basically it looks like this. I think it's like this. If row is less than 3, then that means it's going to be blocks 1, 2, or 3. Okay, do you agree with that?
Yes.
Because row's starting at 0. So then what we need to do is we need to say, okay, if column, it doesn't matter what row we're in, it's now just the column. If column is less than 3, then what block are we in?
Then we're in the first block, right?
Okay.
Oh yeah,
Else,
because 3 is really kind of column 4. Okay.
Else, if column is less than 6, so now we're looking at, so this is else, meaning we're not less than 3, which means we're either 3, 4, or 5. If we're in column 3, 4, or 5,
then we're in the second block.
Good. And then we have just a simple else down here because we don't need to check. And what block are we in down here?
We are in block number 3.
Right, 3, like that. Now.
Wait, but we don't know if this is true, right? Because we don't know about the row. Oh wait, no, because we're going through. Oh.
I just asked if row is less than 3, but look what we can do here. Look, I can keep going on this, by the way. I can do this, and then I can come down and say else again and do this if row is less than 6, and keep repeating myself.
But.
See it? If I repeat myself, do you see what's happening?
Yes.
And then I do this, and now I may change this to what, 4, 5, or 6. right? And then I could keep going one more time. We need one more else, although this one's a simple one because now we know we're at the end, and then this becomes 7, 8, and 9. You see that? Are you
Yes.
in agreement? I could do that. Or, check this out. Instead of having all that code, which goes from line 19 down to line 39, so about 20 lines of code, instead of doing all of that, I can do something a little bit different. I could do this. I could create a variable here called row offset, and I can set that equal to 0. And then I could say, or maybe I could not set it to anything just yet. And then I could ask the question, hey, if row is less than 3, I can say row offset is equal to 0. Like this. Okay? Then I can come down here and I say, well, else if row is less than 6, then row offset is going to be something else. I'll let you think about what that's going to be. And over here, I'm going to say this, row offset plus that. That's what I'm going to do.
Row offset would be equal to 2, right?
Well, let's think about that. The first time through, if we get it, if it's less than this, it's 0. And so we get 1, 2, and 3 for the blocks. The next time if we make it a 2, well, 2 plus 1 is 3, we get another 3. We already ended with a 3. We need a number, we need something that goes 1, 2, 3, 4, 5, 6, 7, 8, 9.
3.
It's 3. Right there. And then we need one more else. Oops. And what's the final row offset going to be at the end of that else? Is the question. Right down here, what's this value going to be?
6, right?
Yeah, 6. Exactly. And so now we have, instead of going, from whatever, we go from 19 to 32. So we've taken out 7 lines of code, and it's a little bit easier.
Yeah, we might want to even declare it as a method so that it's just a bit easier to read, to know what it is.
Yeah. Hold on, I just see there's a read-only property called row. Got a slight problem there.
Yeah.
Who's using this? It's used here. Text value change. I'm going to change this. I'm going to rename this to grid row. So I'm okay using it here as the way we're doing it. And this one I'm going to rename it to grid column. Like that. Let's go back to see where row is being used here. Okay, good. Good. Next, I want to now declare these. So let's declare these. Actually, I want to change. What happens if I change Sudoku square to iSudoku square? Is my question. I'm wondering.
I don't think that will work, because
Let's see where we break.
their
Selected-
ancestors are both different, right?
Selected square. I just want to see. No, they are Sudoku square implements iSudoku square. So I kind of want to see what's happening here. Selected square. I just want to play with this because I want to switch over entirely to the interface and see if, how much do we break? I'm looking for errors is what I'm looking for. It looks like I got 8. Got a problem where we're looking for the background. Block, and clear. We're looking for clear. Clear notes. Okay, so we got a lot of errors in there.
Yeah.
Yes.
Is it mainly only on the selected square? Let's see if it's only on selected square. I want to see how do things drop if we change it to that right there. This, if selected square is just a Sudoku square, Then I'm going to go in and do that, like that, show selection. And I'll do the same thing here to just kind of break it out. Should do the same thing here. So just doing these is checks on it, just so I can typecast it back. I'm just doing this test camel so that I can, oops, this is the wrong name here. I need this to be a different name. Do that. Okay. All right. Then we'll return this as a Sudoku square. So now we've got Sudoku square, select square still of type Sudoku square, but we've got the selected square we've changed its type to an I Sudoku square, which is a much simpler thing. It has only value and notes. And I'm just trying to simplify and break these apart to see when my errors are. Still bad? Let's see, what do we have here? Cannot implicitly convert type. Do the same thing here, I think. Yeah, bear with me on this, Campbell. I know this might be a little bit like, wait, what's Dad doing? Right now, I'm just kind of making a lot of changes to see what architecturally the impact is going to be. That's kind of where I'm at. These are going to be all I's. And move characters from group. This is going to be an I in here. It's coming in. There. What is going on with that kid? This looks like it's going to be an I as well. And that's going to be an I. Keep the block. Okay.
Wait.
What else do we need? What'd you say? What?
Why do we have to change all of them? Don't we just have to change the one that we're accessing from the,
Well, we're changing all of them because they're all being passed into our solvers. And instead of passing in a Sudoku square, I want to try passing in an I Sudoku square piece because it is, it's less heavy is what it is.
okay.
So that's what I'm trying to do. And I'm trying to explore to see if this architectural change is going to be prohibitively complex or not. So here, fill from all notes. Here we've got a problem. Fill from notes if possible. Now, one of the things we can do here is we can come in here and say, let's declare the method. So we just declare it in the interface. And that can kind of solve that there, which is also what's cool about this, is it lets us know what do we need at the very least to make this work, regardless of what interface I present this in, right? I could present this on a text terminal or a printer, printing out only the Sudoku pages if I wanted to. Different from WPF, right? I could present it in virtual reality in 3D space, but whatever these things are here, whatever ends up here is going to show me what I need regardless of what the user interface medium is, right? I could transmit it mentally to you using pictures, right?
Yeah.
But what I want is a collection of properties and methods in here. So I'm exploring the architecture is what I'm doing by making this change. So I'm just going to see, I've got more errors now than I had before, but I'm just going to kind of go through the different errors, take a look at them where they are. Now here, I've got value change, square with C focus. These are events that are specific to the user interface. Here, I want to do a conversion here locally. I want to do this. So I want to say, hey, if squares is I Sudoku square, or sorry, not just a regular Sudoku square, give it that name, Sudoku square. Then I want to say square.value change and that right there. I want to do those two pieces there. So just changing the code up a little bit, getting rid of my errors, so I can the ultimate goal of this is to explore and understand what do I need to make the logic work, and only the logic work. Because then I have something lightweight and simple here. That's kind of what I'm doing. So it's kind of a lot of what we call refactoring. Set text, no internal events, that's definitely, this is coming from Sudoku board. Okay, so if I see an error in Sudoku board, I want it to be low level, whatever it is. So I'm going to come in here and I'm going to say, let's declare it as a method, is what I want to do. So let's go back to where we were. Can I do it? Control dot, declare the method. And so there it is right there, set text, no internal events. If I tap to next reference on it, it should now get to the one inside the XAML implementation.
Oh.
Right, but the idea, Camel, is that I'll take the XAML out and I'll put in my virtual reality Sudoku board. Or I'll take the XAML out and I'll put in my printer interface or my console app version of it where I'm just printing out characters in text. So I'm going to take out one, maybe I'll take that out and I'll create a website instead. The thing is I'm taking out the XAML, but the piece I keep always is my iSudoku square. That's what's going on here.
Yeah.
This one's a little worrisome to me because it's a very specific method. No internal events. That kind of is an event. This is basically shutting down the events of WPF is what this does, as I recall. So this one's a little bit sketchy, but the cool thing about it being here is that we're like, wait, what? What? This method maybe shouldn't be here. And it gives us a good hint in terms of what we need to refactor next if we want to make this really high quality code. And why would we want to make the code really high quality? Maybe we're going to sell out the app. Maybe we're going to make money from it. Maybe we're going to save lives, right? Those are reasons, all reasons why we want really high quality code.
Maybe being able to solve a Sudoku puzzle in not that much time will save lives.
Right, sure, exactly. Right, and also by making it very lean and lightweight here, only the pieces we need, that can help us with how much time it takes sometimes. Okay, all right, so let's see what's going on here. Check for conflicts. This, I think, can be all eyes. That can be all eyes right there. Text this square dot get text. I'm gonna throw it, I'm gonna declare it in. I'm going to put it in here. We might as well have a get text method on iSudoku square to get its text. Although, shoot, we've got a value right there, char. Let's go through get text. Yeah, I guess I'm not going to worry about it. Oh, it's sketchy again though. Yeah, this is something that happened as we were writing this. We had a char versus the string, and this get text method has got some additional code in it that says, hey, if the char is equal to min value, return an empty string. And then we have code here that says, hey, if it's an empty string right there, then get out. We don't do anything. So we'd have to change this code. So we'd have to basically get rid of, there's some risk in changing this. So what I'm going to do here is I'm not going to change it, but I'm going to throw another to do here that says, remove this and replace with value, updating logic. That's how we do that. So I'm putting it in for now just so I can get through all of this and get through the errors and what's going on here. Looks like this could be maybe changed to an iSudoku square. Show notes for square at. Ooh, we've got an is empty. That feels useful. I'm putting that in here. Okay? So, yeah, kind of the question is, what do I decide to put in here? Show notes for square at. It's called, there's an I right here as well.
We know there are more errors.
Square dot show notes, set notes. Fine. I'm declaring that one. That one feels useful. Although I'm going to say the name of this variable is going to be called notes. What'd you say, Kimmel?
I'm just counting the errors.
You counting the errors?
Yes, I'm seeing with each fix how many errors.
Select square. Selected square is equal to this. So this is my selected square here. I guess we got to say as. Now, you know what I'm going to do instead? I'm going to create a method called select square. We'll pass that in. Okay. Do the same thing down here. Like that. Just declare that method. Select square, and then we're going to say select square is equal to iSudoku square as, and this is a typecasting. I don't really talk about this. We're typecasting one thing to another. And because the class implements the interface, the other. One implements the other. I can actually do this and it'll work.
Oh, okay.
Sudoku square. So what happens is I still get something that functionally is the same. So far I'm only refactoring right now, and I'm refactoring just to get, and I'm still in this process of exploring right here. I've got a set text column square. I think I'm gonna throw it in there. Set text. Remove this. And should I also remove? Yeah, remove set text and get text. Yeah, this is our problem. So we created a problem initially, right? What's happening is we're doing this, we're realizing, oh, there are things that shouldn't belong here. Like, in other words, I have get text and set text, which are the same as assigning to value and reading from value, right? We used one for solving and the other was for the interface. These, in the process of fixing the bugs now and doing this exploration, we're now seeing problems with the architecture that we didn't see before, right? The reason this was problematic is we have a bug, we have to fix it in one of two places, a bug related to this, right? And that's problematic. We've got to go search and find our way through. So that's kind of what the justification is for this. All right, what's going on here? Row, does not contain definition of a row. We still got to define that. Let's go declare that. That's one of the first pieces I wrote. So we're going to put row in there. Good. And we're going to throw column in there. There's column. We're going to throw block in there. There's block. Now we're getting a much smarter Sudoku square.
Yeah.
We can now ask it, what row are you in? What column are you in? What block are you in? Right? Are you empty or not? Right? Got some other methods on it as well. Set notes, super valuable. Fill from notes if possible. We got that. That's pretty cool too. Okay, go on. Get square position. With this Sudoku square coming in. What other problems do we have? No other problems. Sweet. Although, now we don't need this anymore. See what this code is doing? Iterating through rows and columns. Checking to see, hey, does this square at this row and column equal the one you're passing in? If it is, pass back the row and the column. We're already setting that now in our Sudoku board in my static constructor. We wrote this code right here just minutes ago, Campbell, where we go through, we set the row, the column, and we figure out the block.
Yeah.
So, because those values are there, right, we could rewrite this method to simply just say, I don't need this anymore. I can simply say, row equals the square dot row. Similarly, column. Whoops. What's wrong in the code I've written here? It's not this anymore.
Wait.
What goes before the dot in both of these lines of code here?
It's Sudoku square, right?
Nope. Sudoku square is an interface. It doesn't have any values. You need an instance of something. So not this, but you're close.
Would it just be square?
It would just be square. Because now we have that data. In fact, now that we have that data, we kind of really don't need the R and the C anymore. We don't need to even pass it in here anymore.
We might want to keep it in there just because if this ends up not working out, to get back to it.
I think that's a great idea. And you know what I do in situations like that, when there's a really great idea like that in my head? You know what I do? Just say, yeah, you can totally do that. Or I'm just going to delete it and we're going to just go forward like crazy. So I'm going to now go forward like crazy. But don't worry, we've got everything in version control, right?
We could at least comment the code out instead of.
So now I'm going to come in here, and when we passed in C before, we're now going to use square dot column. I know you're worried. Don't be. Same thing here. Square dot row. By the way, this could be the show where I get my comeuppance finally. All right, see what's happening? Because we already have the R and the C there. We don't need those anymore. All right, so now that works right there. How are my errors doing? They're jumping up all over the place, going up and down in this, right? A lot of changes here. Does it have a test value? Should we put that in Sudoku square? I'm going to say yes, but I kind of want to say we need a better name than has test value. It's the brute force attack, Campbell. This is where we're laying that down. Tell me what you think you should do here. What are you doing over there? Hold on.
I'm testing something out. I'm testing something out.
Let's go check out, see what Campbell's got on this machine over there.
And wait.
You need to have the types for those. So you need to preference each of these with a type like int.
This isn't permanent for the code. I just want to see. Can I?
You need to have a different name for the second variable.
Oh, right.
No, if you want to comment it out, you have to include the comma. Tell me what you think.
You can put comments inside. Ooh.
You can. Did I show you something else?
So we could have just commented out the code for that.
We could have actually done it. Can I show you one more thing? That comment you got that you put down there, I think that really comes to e447.
I am.
Where's my chat button? I gotta go. There's my chat button. Just realized my chat is not. I don't have the chat room up. Over here. That over that. On the other side. Okay. Oh, here's what I was going to show you, Campbell. Back on your machine.
Oh.
If you want to create that comment, you just type in 2 dots in the space bar. Coders will give you
Oh.
that. Okay? All right. Yeah, you're right. We could totally comment it out. All right, back over to my machine. We're making decisions, man. Stay with me on this.
Okay.
I've got has test value. Do I want that the question is, should it be in Sudoku square or should it only be in the user interface? Has test value is when we do the brute force attack. Since do you have a comment on that?
I think we're going to have to put it in Sudoku square because we want to also implement our logic into the brute force attack.
So that's the decision-making process here. So has test value is now there. Okay, cool. What else do we have here? Has conflict. Has conflict.
That one is it's checking to see if the answer is correct, right?
Yeah, I want to make sure there's nothing else in there. I want to see what's going on with has conflict. Who's implementing that? How are we implementing that? That's in main window. Has conflict is here. Oh, it's just a property. It's a property. I'm totally fine with it. We're gonna, we need to move that as well into here. Now here's the cool thing. So check this out. This is what's so sweet and beautiful about this. See right here, we just added has conflict. It's a Boolean.
Yeah.
Right? See that? Now check out over here in main window. Main window has got, oops, sorry, not main window. Sudoku square has this property called has conflict. It goes from here to here. It's got a simple getter that just gets the value. But look at the setter. If it's the same, don't do anything. Otherwise, okay, we'll set the value. And hey, if we have a conflict, what do we do, Campbell?
We changed the color of the selection on both of them.
We change the color what?
We changed the selection color on both of the round numbers. Or not selection color, the background.
Yeah, well, this is in one single square.
Yeah.
If this square has a conflict, it sets its background to that color right there.
Yeah, so it affects both of them.
Right. What's cool about this is in the user interface. In our virtual reality version, when there's a conflict, we might send an electrical signal to the subject's body to shock them. Oh, dude, maybe we shouldn't be pulling on our gum on the show while we're being recorded.
Okay.
That's just like a pro tip I'm thinking we might want to consider. padding. I'm not saying we don't have to do it. I actually thought it was fun that you were doing that. But I was just thinking, What do you think, Genescu7? All right, so, but the cool thing about this, though, let's not lose sight of that, is that in this interface, I make the background red. In the virtual reality one, I shock the user, right?
Maybe we don't shock the user.
Okay, don't just a light voltage, maybe?
Maybe no
What about
voltage.
like a flamethrower out in the yard that just goes?
No, I think just like a...
What about like a bucket of cold water? The cool thing
Well,
is,
the cold water would ruin the VR.
okay, so yes, I'm hearing yes on the bucket of cold water.
No.
Bucket of cold water, right? This is the thing, right? Software can control hardware, right? So you can dump things on people if you wanted to do that as part of the user interface. We've got the whole thing decoupled. The interface, even though I've got more errors right now, it's not compiling, we're getting closer to something that genuinely feels better to me, right? We're separating the visuals from the logic. And that's the essence of, I think, some really good design. Okay, so let's see. Let's keep going, searching through those errors we have. We're down to 7. That's not bad. Okay, here. We're setting the background color. Ugh. We're setting the background color. We're doing it from here. In this case, I'm going to do this manually right here. I do not want background color to be something that our Sudoku square knows about. It shouldn't know about background color because it could live in a virtual space. It could live in a 3-dimensional space, a 4-dimensional space. We might create 5-dimensional Sudoku, right? For 5-dimensional creatures, right? So we do not want to set background color here. So we don't want to set it through the interface. We don't want to put it here. Nothing related to UI should be here, okay? So what I'm going to do here is I'm going to now say if it is a Sudoku square, then I'm going to create an instance of it right there. And if that's the case, then now I can set the background on it. So now I can do my very specific UI call here. UI change.
Okay.
Right? And that is and this is the iSudoku square. And I'm just asking, hey, is it one of the ones I know? And what we should almost really do is rename this to the XAML Sudoku square.
Okay.
So we know it's totally XAML. We can try it. I've had problems renaming. Let's try to see what happens. Just jumped up to 36 errors, 6 errors, down to 6. Okay, cool. All right, good. Yeah, sometimes I've had trouble renaming the controls, but it looks like we're good on there. Did it rename? It did not rename this file. But it did rename that. Let's do an F2 on here and call it XAML as well. Oh, shoot. F2 XAML Sudoku square. So now we know it's very much in the XAML implementation of this.
Yes.
Okay, what are we doing? Clear.
Ooh, I think we might.
I think clear goes in, and implementation details are elsewhere. So we're going to throw clear in there. Clear goes in for sure, I think. You okay with that? Did you have any comments on that?
No, I was saying it should because it isn't.
Yeah.
It isn't really the UI.
Yeah. Same thing for clear notes. Clear notes is not really specifically the UI. We're not saying, oh, you've got a background, right? That sort of thing. So there we've got clear notes and show notes for square. That needs to take an iSudoku square instead. And it looks like it all still works because get text is on iSudoku square. Right, so that's good. Looking like we're getting really close to being done. Locked. I think locked should be part of it.
Yeah, that would make sense.
Right? So it can be locked. It can be locked in any dimensional representation of it. It can be locked.
Yes.
Okay, this one can change to iSudoku square. Look at this. Show notes for square at. Well, we don't need what's the row and column. We don't really, well, I guess we got them, but we don't really need them. Yeah, we don't need them. So all we need to do here is we took those out. All we need to do is take out row and column here. Okay, we have a set of tests that we kind of perform. Uh-oh. Yeah, this. Because I renamed this right here, it can't find this. I think that's an app XAML. Is that right? Is it in app.xaml.cs? No. Where are we? Did I miss it? It's the main window XAML. Let's go to main window XAML. I may have to rename this back if I can't figure this out quickly. Find Sudoku square. I can't find it. All right, I'm going to rename it back. I'm sorry, Camel. And I think that's going to fix it, so it'll run. Let's run it now.
We have a target project.
What'd you say?
We have a target project.
Object reference not set to an instance of an object. Ah, squares. It only has nulls in it. All right, so this initialization should not happen here. It needs to happen a little later. This is that initialization code that we just wrote. So I'm not too worried that our first issue is here. I'm just going to take this and and extract that. We'll call this initialize squares. Maybe just initialize like that. We'll make it public. And I'm going to get rid of this. Next, I'm going to call initialize after we assign all the squares. So I need to look at where those square assignments are. You just got, oops, is that it? Add square. There it is. So see this camel? See all this code? This is where that code we wrote from before. At the very end, I'm just going to call initialize right here.
Oh,
see that?
that we used a lot of shift enters for.
Right, exactly. All right, let's give this a try. Row.
Yeah, I think it would have been very hard to do this
Ooh.
without using shift enter.
We got these three pieces we have not added any data for here. So we have to be able to save these. Okay, we've got these pieces, so we need to add these. So row, column, and block right there. This is the code that was generated for us. We don't need that. Save, delete, stop, restart. Try it now. All right, I would call this good news. What do you want to do to test it out? Tell me what to do.
Well, I'm not sure because there are multiple things we need to test out, right? Yeah. But so I think we should load up the easy game, test out how solve works.
Okay.
And then load up, maybe even still the easy game, and then get it to almost solve, and then try the brute force.
All right, so we'll start with the easy game. Load that up.
Solve.
All right, so far so good. Just hit solve.
Yes, I think. Yeah, okay. Now try hitting solve again and then brute force.
Solve again. And now hit brute force.
Yes. Okay.
And then maybe undo.
And then
Look at that.
try
Isn't that
redo.
nice? And then redo. Okay.
Yeah.
So that's not bad.
Should we
Rec
test
Runs
out
This is
clear
out there, asked the question, hey, any chance you can help me understand what type of programming language would be best used for making a CSGO gambling type website as a mobile app? I'm gonna have to say probably no. I'm gonna say no on that. I do not have enough knowledge to be able to give you any recommendation that I would say to be high quality. But I wanted to at least address that. Okay, so it looks like this is all good. Now we still haven't implemented the new logic yet. Do you want to run more tests?
Let's try, I think, clear notes. Well,
Clear notes?
not now, but if we load up the easy game again and then hit solve once. And then clear notes. Yeah, okay. Then I'm not sure.
And it adds things, and do we see them highlighted? They do. That part looks good. I'm control clicking on here,
Control.
hitting solve. Solve. This is the one we don't finish. Is that right?
No, we finished this one.
Okay.
Only the control alt shift one we don't finish.
Is that true? Can we see your notes? I thought there were two. I thought I was looking at them this morning. Can you show me the benchmarks?
Well, yeah, one we need a hint for, but the medium thing
Yeah.
we can do.
Yeah, I thought we could solve 3 of them with all of our stuff. For
Yeah,
some
that's
reason,
what
that
I
third.
thought as well, but
I wonder if we had some sort of regression. We went backwards into something that wasn't working. So the hard
Yeah.
game. What do you hit for the hard game to bring it up? Control Alt.
control shift.
Control Shift. All right, let's try that. See what's happening. Control Shift. 1, 2, 3, 4, 5, 6, 7, and that's where we're blocked. It's 7.
Yes.
Okay.
And then we take a hint, and then we can solve it.
What'd you say?
And then we take a hint, and we can solve it in 3 solves.
Yeah.
And if I remember correctly, the hint is relatively quick, I believe.
So take a look at this. Wait, hold on. Is this right or not? Yeah. No. I'm just trying to see if there's something in our current rule that we can see here, but I don't. All right. So let's go back and do the logic here. So what we need to do is we need to now that we're storing the groups that these pieces belong to, like the block, rather, the block number, we need to now collect all the numbers within a particular block and group those into sets is what we need to do. So basically what we're talking about is a dictionary of lists. The list is 1, 2, and 3, a list of ints, right? That's gonna be a dictionary for keyed by like B2. Another one keyed by B1. Okay? To make it easier to read, we might make it the dictionary keyed by strings. So we just have B1 is a string.
Okay. All right.
Something like that. Let's go back to our n by n solver. Wait, let's do this. I think I'm going to check in the code for a second. I'm going to check in the code. We're going to call this refactored to isolate or decouple.
And then I'll actually fetch and pull your.
All right, cool. So we're refactoring to decouple our painting logic, our drawing logic, our UI code from our Sudoku solving logic. So that's all we did. Let me stage all of those, commit those out. Campbell's getting those over on his machine over there. Okay. Back over to my machine. Let's start making those changes. So we want to go to our n by n solver. There it is. So we need to add the new logic. So if the group count is a column or a row, cool. That's what we want to do. First we want to do this step here, which is collect numbers by block. See it?
Yeah.
Okay. So we're going to go through every number. Hold on, let me refresh my memory in terms of what's coming in here. What is indices? I've forgotten completely what indices does. And I'm thinking, well, that's not great. It either has a bad name or or there's just too much complexity here. We got to, the code needs to be easier to read.
Isn't it what we index the,
Oh, it's the indices of the ones to try.
Yeah.
Okay, so now what I'm going to do is I'm going to now give this a better name. Indices to try, indices to check. I'm going to call it that. And then I'm going to also, in solve for many, I'm going to do I'm going to do this everywhere. So I'm renaming these, this local variable, so it's easier to understand. Renaming this one, and then renaming this one. Okay, so these are the indices to check. So we have n squares that all contain n notes or fewer in indices to check. Right? So see what I do when I go back and I look at code and I'm like, wait, what is this doing? And I have problems. Sometimes I'll rename something like I just did.
Yeah.
So that it makes more sense the next time. Like I definitely know what group kind is, and now I think I have a better idea of what indices to check is. Okay. By the way, at this point, when you see a comment in code, it's often, your indicator that you want to do an extract method. So what I'm going to do here, since we actually have this in this point, I think what I want to do is take this to the end and put it in a second method, is what I want to do. So this one is going to take, let's see here, it's going to ref in the result. I guess I'm okay with that. Indices to check, group kind, all note numbers is coming in. And I need to figure out what all note numbers means as well, because I'm not sure I like that either. And then we're going to say solve for many with known indices, with good indices or something like that, with indices to check, maybe something like that. I don't know. I don't have a great name for this yet, but I do know that I'm like that I kind of want to stop this one in terms of being easy or hard to read. What's this do up here? For each one in here, get the numbers, add the note numbers. If the count is less than here, the count is greater than. This just verifies that. This verifies all of the. Can I extract this at all? Is it going to let me do it? It won't. Square note numbers. Let's get notes for it. So we're going to see if it's greater than indices to check. So this is basically I want to do something like this. I want to pull this out to its own method. It's not letting me extract it easily, but I want something like this. If indices if note counts are all fewer than, and then we're going to pass in something there. I'm going to do this. Note counts are greater than. And now note counts are sufficient. Note counts are sufficient. I think I like that best. And I'll say if not, then we're going to say return solve result none. And then let's go declare this. And what do we need to pass into it? We need to pass in indices to check, group. Say return false there. Otherwise, we're going to say return true. So what do we need to do? Group and indices to check. That and that. Those are the two pieces we need to pass into it. Not the one in the middle. And then that means in our calling code, we need to pass those two pieces in as well. Okay. All right. Okay, so now our main method. So this piece, I'm going to move this down. I'm going to just drop it down a bit. But our main method now is looking arguably a little bit easier to read. If, hey, the note counts are not sufficient, then we're going to return solve result now. Otherwise, we're going to call solve for many with indices to check. Oops, all note numbers, we needed that to get that out. So all note numbers is, I think, going to be an out
Wait.
parameter. Go ahead, Campbell, what do you want to say?
Why are we changing? Oh wait. Oh, never mind. Sorry.
No, I'm kind of with you. Like, wait, why are we changing this? I'm changing this so I can make this easier to read is kind of where I'm doing this. Out, and then all note numbers, like that. So now I've got all note numbers passing in. So now basically, at least it's easier to read, right? If note counts are not sufficient, then we're going to return solve result.now. Otherwise, we're going to solve with many indices to check, which takes us down into here. Okay, cool. And now we need to still add the new logic. And this is the old logic here that we still want to keep. This logic is going to be, I'll keep it here for now. Let's do this. I just want to run to make sure that everything's still cool. Everything still works as we're expecting it to be. That's a good sign. Let's load the game. That's a good sign. Solve. That's a good sign. That's a good sign. 1, 2, 3 clicks. Just what your benchmark matched, right?
Yes.
Okay. So no changes to behavior, only trying to make things easier to read.
Only refactoring.
What'd you say?
Only refactoring.
Right, but the refactoring did help us. So we know indices to check has a list of indices that we need to check inside of here. And we know at this point that we have good indices to check at this point. At this point, these indices match the pattern. All of them contain between 2 and n of the numbers in our group. All of them do in each of these squares. So now what we want to do is we want to go through all of those squares, all of those indices out of group, and we're going to. Oh wait. Let's go back and look at this picture again so I got this right. So now, say this is our group, right? And our indices are going to be 0, 1, 2. We've got an index of 2, an index of 2 right here. That's a 2, meant to be a 2. We've got right over here, we've got an index 3, 4, 4, and we've got an index over here 5. Okay, those are our indexes. Let's make those red. Okay, so that's that. Those are out of group. So what that means, this is actually equal to group of 2.
Oh.
That's what it's an index into. Okay, group is this parameter right here that's passed in. Okay,
Yes.
that's what's going on. So it's saying that's group of 2, this is group of 4, and that's group of 5 to get to those squares. But we need to go through just these pieces here, these indices to check. We need to go check them out. We need to basically say, hey, look, let's do this. Go through each index to check. So we'll call this index right here of the square. And now we're going to go into group. We're going to go into group here. There's a group of index. That's an Sudoku square, which now has a block property. So we know what block it's in.
Okay.
Okay? So now we need to have that. I'm not sure why I need this. If I need that or not, I'm going to comment it out. But now we need to now create a dictionary of lists. Is what we want to do. So a list of integers looks like this. I like that. If I cut that to the clipboard, I can now say I want to create a new dictionary of string indexed what's on the clipboard. String, or do I want to make it an int? Maybe I'll make it an int, like that. And so that'll give me my dictionary indexed by ints. The int I'm going to use is the block number of, and then it's going to have a list of integers. The integers I'm going to have are these right here, which are what are the notes in that square. I'm going to put them over inside it. That's what I'm going to do. So we'll come in and we'll say, okay, Here's my dictionary. We're going to call this the block map. Kind of like that name. So now what we're going to do is come down here and say, hey, look, if the block map does not contain the key of this block, then we're going to go ahead and say, hey, block map dot add, and we're going to specify the key again. Here's the key, and what am I going to put in? I want to put in a new list of ints, like that. It's empty for now, but I'm just doing that, okay, in the block map. Okay, and I've added it by this right here. This is showing up more than once. See it in there? I'm going to come in here. I'm going to hit the coder's key and choose introduce local for all occurrences. See that right there? All occurrences?
Yes.
For all occurrences. And then I'm just going to call this the block key. Maybe just the key. Okay, cool. So if the block doesn't contain the key, then add it to the block map. We'll add that piece in. With me so far?
Yes.
Now we know for sure, no matter what, that this is going to work because it's got it. So now I have my list of ints, so I can call a method on list of ints, add an item, right? So now I can add the ints. Well, how do we get those ints? We need to go to the notes, I think is what we need to do, right? We need to say, go get the notes, right? What do we have a notes? We've got a notes. This is a string, I think.
That's a, oh yeah, no, it's character. Oh, it is.
It's a string of comma separated pieces, right? Somewhere in here, we've got a call to split them. Where is it? Where's my call to split? I have nothing with the word split. What if I added the word notes? Clear notes, click to the fill from all notes. Look for something that returns.
Once we finish this, there's a bug in our code somewhere that, and it's a problem with the characters that you can put in the Sudoku.
Oh,
here.
right. Yeah,
Yeah,
you're right.
I'll show you.
I know exactly the bug you're talking about. Do you want to take a break from what I'm doing and go show
Yeah,
that?
just for a second. Which?
Go ahead.
No. Yes.
You got build errors.
Me.
Looks like you've got, click on the arrow. Say no, I don't want to, don't run the last. You got you added some code in here that you don't need. See right where I'm pointing?
Oh.
The R on the C.
Oh wait, this, I thought I deleted it. Thought I got rid of it, okay. So we should only be able to put 1, 2, 3, 4, 5, 1 through 9, but we can also put letters and characters.
Yeah, somehow we got a new bug.
Which it worked before. On
Right,
code.
so we added a new bug. We'll have to we'll hunt that down. All right, switch back over to my machine here because we're running a little bit out of time, and I want to make sure we get close to fixing this if we can before the end of this whole thing. Where's my solver in by end? There it is, right there. So we have this call. I found it. It's called get numbers, and it takes the notes like this is what it does, like that. And since base group solvers and answers for this, I can just call get numbers like that. And essentially what we're going to do is we want to add that whole list. I think, is there an add range? An add range, can it take that? Will that work? I think that'll work, but you know what? We want to add it slightly differently. We only want to add it if it doesn't exist in it. So we want to get that kind of union effect. So what we really want to do is do this. We want to for each note in here, we want to then check to see if block of key. Let's do this. Let's create a variable here. Call it block notes. All block notes, maybe like that, is equal to that. So now we don't have to do this code anymore. And so now we can say if all block notes dot index of notes is less than 0, meaning it doesn't exist. And we're going to say all block notes dot add. So we're only going to add if it doesn't exist. Add the note. Okay?
Okay.
All right. That is now this step right here. At the end of this process now, we need our dictionary, our block map to contain at least 2 entries. So we'll say like if blockmap.count is greater than 1, then we can do something with that. We have to be able to subtract. I'm going to set a breakpoint here and just kind of let's see where we get. I'm going to run it and see if we get the breakpoint. So we're up here, load game, solve.
We do.
Okay, we get to this point. Cool. We have 2 blocks. We have a block 1 that has a 1 and a 2 in it. See those right there?
Yes.
And we have a second block that has a 1, a 2, a 3, and a 9 in it. Sweet, that's exactly what we want. Now what we want to do next is we want to do the set subtraction. And we want to basically go through every block in here and then subtract the other blocks and see what's left. And so that's what we want to do. So what we need to do is we need to go to the block map.
This might slow things down if we're going through each block.
It won't. I can almost assure you it will not. Because we're dealing with really low-level objects, creatures, objects here. We have an incredibly fast machine. Things get really slow when you start doing a lot of things, but we're not doing that much here. So I'm going to go through every key in the block map keys.
Oh yeah, because we're not. I was thinking about the brute force, and in the brute force we go through each one multiple times for each value in the first block. But for this one, we're only going through it once.
Yeah, I think this is going to be very fast actually. So we're going to say that's going to be equal to, that'll be my target block. Let me do this. Let's declare the local for it. And I'll please do my name. So there, target block is going to be this guy. Then what we want to do is have a second one. We're going through the loop again for every, we're going to call this, give this another name, for every source key is what I'm going to call these. So with this idea, we'll keep this idea of source and target. We're going to go in through that. And then in here, we're going to call this the source block. So we're now going to start subtracting if it's not equal to the target block. So now at this point, if target block is equal to source block, then we're going to continue. We're not going to do any more logic. Down here we need to subtract. Like that. We also need to hold a list of what the results are going to be. So I think we need a list of ints that's going to be our results. Results for this subtraction. It's going to equal to a new list of ints. Okay? Those are my results. Okay?
Yes.
And what I need to do is I need to make them equal to whatever's currently in the target block. Okay? So, I think I can do like a to list here on this. That'll clone it and create a new list. Pretty sure. So we can make changes to this without changing that one. So we're going to start it out so it's equal to this, and then we're going to go through here and we're going to check to see, hey, if we're subtracting, we need to take it from there. So we need to check to see is, hey, if this dot index of the piece we're trying to subtract, which is going to be, well, its source block is a list of ints. Holy cow, we need a new for each down in here. So yeah, look at this. We've got nested for eaches like crazy. This one's finally down to a note down here in source block, right? So what we're going to do down here is we're going to say, for each note in there, we're going to say, hey, look, if the results for the subtraction, if the index of the note, if it's greater than or equal to 0, that means it's in there. If that's the case, then we're going to say results for the subtraction dot remove note. Remove it. Okay?
Yeah.
That's what we're going to do. Now at this point, I think subtraction for this block is done. For this block is done. I'm pretty sure. And if that's the case, then if there's anything left in here, that's our magic point here. So if this dot count is greater than 0, I'm pretty sure this is magic, meaning we can remove these from the target block.
Oh. Oh.
Okay, from the other squares in the target block.
We would be able to.
What'd you say?
Just like what we were talking about in our basic
Yeah.
understanding of visual.
Yeah. We can, so basically, if we get anything left, like a 3 left over, then there's no other 3 in the other B2 squares, which means in this group down here. Does that make sense?
Yeah.
There's nothing there. Okay? So, we're kind of hoping for a breakpoint there. That's what we're hoping for. Let's run it. Ooh! I got 2 in here. I got a 3 and a 9. It says I can remove a 3 and a 9 from the other squares in the target block. Target block is here. It's got a 3 and a 9 in it. The key is 7. What block is that?
That is block number 6, right?
Yeah, I think it's actually going to be 7. That's what I think it's going to be.
Oh.
I think our block numbers for outside world, we made those numbers 1 through 9 to match. I'm pretty sure what's happening.
Oh.
Let's
Okay.
see. That's what I believe is the case here. The key is 7, so block map of 7 is, that's the dictionary. The dictionary piece, where is my dictionary? There it is there, block map. There's the add call, the key is the block number. Yeah, so the block number is 7 for that group. Okay, so at this point, we can remove those other squares from the target block. Now we got to get the target block. We know that the key for that is 7, I think, right? Is that right?
Yes.
Yeah, the key is 7. So we need to get block of 7. Somewhere in here, I think in the Sudoku square,
Where?
Sudoku board, we've got to get block. Shoot, I thought we had to get block. Let's get block. What'd you say wait for? Ah, it's the main window.
It's just a bit confusing. Or it was. Now it's a bit. Huh.
Yeah, because we don't have a visual. I totally am with you. It is confusing. I want to take these 3. I'm pretty sure I want to move all of these up into the board. See those 3? Those belong in the board.
Yes.
I'm going to delete those. I'm going to kill the app. I'm going to move them back over to the board because we need to be able to call them from low-level stuff. So we put them in here. Whoa, that's not what I wanted. Oh wow, it didn't take my cut. I should cut something at the end. Looks like I cut something right at the end. Okay, there it is right there. Just get column, get row. What's going on here? I'm going to declare instance method. Okay, that's okay. Change it to static. Static. Static, and I also want them to be color. Okay. All right, so there's get column back over here. We need to fix up some bugs anywhere we were looking for get column, get row, get block. We need to go to the board to get it. Sudoku board. You understand that change that I made right there? Are you like at a point where you're like, dude?
I understand.
You got it?
I got it.
Okay, cool. Let's see what other errors we've got. Probably similar ones. Get block. There you go. Get row. But now we're getting a much better engine, right? Moving these methods there. This is the thing that refactoring and sometimes, making changes like this bring you. They bring you insight into what was wrong, what was obviously wrong but still working before, right? So that's much better now. Okay, back to my solver. Now I should be able to add that code here where I can go in and say Sudoku board.get block, pass in key, right? And that might just give me what I want. Now, the other thing that's kind of important, we'll call this the blocks. What's happening here? Oh, it needs a row and a column. Well, shoot.
Wait, why does it need a row and a column?
Because that's how we wrote it. We were going to give it any row and column, and it was going to come back and give me the whole block, which makes a lot of sense. What I need is another one of these called getBlock that only takes in a block index, like this, and then maybe goes from the block index to maybe call the other one, I'm thinking. Return getBlock. And so, for example, if block index was 1, if block index was equal to 1, maybe not block index, maybe make a number. Index means it starts from 0. So block number is equal to 1, we could say get block 0, 0. See what I'm doing?
Yes.
And I could also do like an else if block number is equal to 2. Then I'm going to give it what? This is my row, so my column goes to 3. Make sense? I can do this. I think got to be a better way to do this. But I could do that. 0, 1, 2, 3. No, this. Yeah, 6. Like that.
We have to end this show soon. But I think we're close to solving this, so we might. Yeah.
Yeah, I don't know. There's 4. There's 5. There's 6. And now what happens here is we see something similar. This goes to 1, 1, and 1, like that. Keep look at that, and then we get 2, and this is going to be go back to 0 and 2 and 2 like that. Oh, there's 4, 5, and 6. Is that right? Did I get that right? Maybe I've got something wrong. 1, 2, 3, 4, 5, 6. This one should be 7, 8, and 9. 7, 8, and 9. Then we're going to say maybe if we're down here, we can say some sort of debugger option. We still need to return a value. I don't know. I guess I'll just do this too. Oh wait, this is wrong. Campbell. This should be 3, and this should be 6. Okay. All right, now let's see if we can at least get there. All right, and then we'll end the show, and I guess wait a week and write this in a week. Let's see what we got here. Load game, solve.
Yes.
We're here. Hit run. We get to here. All right, this is better. Okay, let's see if this call now works here. So we want group 7. Block 7 comes back with, what do we got here? Oh, it's a bunch of Sudoku squares. We got to scroll down to see the values.
Okay. That is very.
The value is empty there. Great, I scroll all the way down. So look at this, right? When I hover over this and open it up, see how this all just says Sudoku square?
Yeah.
All of this? Because it just shows you the type. There's a cool thing that you can do. It's an attribute. I forget exactly what it is, but it's, I think the attribute is debugger. We need to use system debugger diagnostics. So let me bring that up here. Diagnostics.debugger. Maybe the system diagnostics. Let's see what we get. When we come in here and say what debugger, debug. Come on, help me out here. Okay, debug attribute C#. What is it? This debugger display is what I'm looking for. Debugger display, that's what I want. Something like this. And so what we can do is by putting in the debugger display attribute like that. Why didn't it give me IntelliSense on that? That's weird. I can now specify a property of this where we can just come in and say, hey, show me whatever value is, like that. Okay, makes sense. And then I can also even come in here afterwards and specify the notes as well. So now when we're debugging this, we can see the value in the notes both showing up. I think it's got a property called notes. Yeah, there it is right there. And then and I think it's got value too. So now let's run it again, get to our breakpoint and see what that debugger display attribute did for us. Solve. Okay, so now go down and get the blocks like we did before. Now take a look at, see the difference? See what's happening here?
Yeah.
Now when we open this up, now we can see what the value is, right? You've got a 6, you know, a bunch of zeros. So nothing's filled out yet. And then a bunch of notes. See all the notes?
Yes.
Right there in parens. So that's very cool. So now we have that data right there. We are removing, what are we removing in the results of this? A 3 and a 9. And it has to be from blocks that are not in the blocks that are already given to us by this group right here. So this group is giving us some stuff too that's coming in here. It's giving us, looks like probably this one right here, which is at 6, into 6. In fact, I bet if you go in here, we're going to see 6 is one of those numbers. There it is right there. See it?
Yeah.
See the 6 index to check? So we're checking 3 of them in here. So what that means is if we find any, they cannot be an indices to check of the original one. In other words, hold on. Group, so we need to make sure that any blocks we examine are not among those already in indices to check. Maybe group, I'll just write this down, group of those indices to check, like that. Because we can't take it away from itself. We can only take from the others. That's kind of what we need to do. So with that, if you want, we can end the show, Camel. I know this last part's been like a little intense because I've been like jumping all over and I don't think I've been maybe taking care of you as well as I should, you know, but you know, I think we're looking at some big picture things, right? We looked at refactoring and kind of, you know, getting closer in terms of implementing this. You want to end the show and get to? Okay, we'll do that. Why don't you let me get a rate going? Let me check in the code first, actually. Let's do that. And I'll run this. We're hitting this a couple times here, by the way, Camel. I just hit at 5, at 5, at 5. So we are hitting this. That's good news. We just need to get the next level, and we get to super level of magic. Let's check in this halfway through. Implementing the new logic. Okay, that's kind of where we are. Move those pieces over. Refactored more, and anything else that we did here? Make code easier to read. Yeah, that's it. All right, stage all, commit. All right, kids, thanks so much for joining us. Let's get a raid going here. I'll send you over to Lana Lux. There you go.
All right. Goodbye.
Bye, kids.
See you next time.